Alright, welcome to the afterwork video. I only have until like 6:30, so let's use the time now efficiently. Sometimes I have like a 10-minute gap between the afterwork video and the and when I finish work at 5. Ideally, I would just start right into it, but you know, burnout's a real thing, so not too big of a deal. So I'm having a problem here that I sometimes have with Google Chrome where it won't open. I can solve that problem by ending the process if I open up my task manager. So I'm doing that right now, searching for Google Chrome. I can also just use a different browser, but okay, so now I've got Google Chrome open. Perfect. So it's time to bring up the drive. Okay, so the lunchtime video, basically I kind of took a different strategy. I just watched a video on Multicast because it's all kind of brand new to me. I think it probably was on the JNCIE-SP. Let's check. Yeah, so Multicast was on there. So I do remember certain things. I remember Rendezvous, like I do remember certain things about it, but it definitely, I would say, is one of my weaker topics at this point. And not only that, as I explained in my previous video, it's one of the more information-dense topics too, I think. So there's just a lot to learn. Oh, nice. So there's just a lot to learn on this topic, and I don't know how much it's going to show up on the test, but let's keep going. So for this after work video, I'm just going to continue to learn about PIM-SM. Ideally, I'd be able to set it up on the live gear, but that has proven to be difficult. So let's see here, we've got IP Multicast lecture series. Yep, so this is what, oops, this is the video I was doing. So I believe he did have some, oh wait, what is, oh, this is Multicast VPN, okay, yeah, so. Okay, so yeah, so if he's doing a hands-on demo, that sort of thing, I definitely want to do that. So, yep, so this is sparse mode. So yeah, it looks like he's got a demo for PIM sparse mode on Juniper routers. So let's see what he's doing for that. Well, so yeah, okay, so this is the shoot. So yeah, I guess I want to just like follow along with this. He's got 1, 2, 3, 4, 5, 6, 7 routers, and then he's got, so I think I'm going to rearrange my topology to look like what he's got there, and then that's going to be what I focus on. And unfortunately, I might need to give it more videos than I thought I would. Okay, so let's just delete and blank everything. Okay, so let's listen to the first part.
Hello and welcome to the next demo of our IP Multicast lecture series about the latest source organization on Juniper. Before we go over the actual scenarios that will cover in this demo, there are a few prerequisites I need to make you aware of. The fix is saying PIM sparse mode must be enabled on all of the Junos routers. So all of the routers that are going to take part in this topology, each of them should have PIM sparse code configured for its interfaces. In Junos, all of this will be done under the protocol split hierarchy. So this is a little bit different than iOS, if you're from that background. It's not done under the interfaces, it's essentially done as if it was any other protocol in Junos. So protocol split hierarchy, select the interfaces that PIM must be enabled on. In our case, we're actually going very, very broad. So instead of going and naming specific interfaces, we will be using the keyword all. So that essentially means all of the interfaces that have an IP address on them will be enabled for PIM sparse mode. And ultimately, the mode has to be sparse. And by doing that, we're essentially making sure that everything on topology is running in sparse mode. Now, this should be configured for all PIM-enabled interfaces, but what does that actually mean? That actually means all of the interfaces that are connecting PIM neighbors, so all of the routers that you desire to run PIM sparse mode on, any interfaces that are interconnecting them, or making them neighbors, they should be enabled for PIM sparse mode. But also all of the stub interfaces that might interface with either sources, anything that may connect to a source of the router and FHR, those interfaces have to be enabled for PIM. And any of the interfaces that might face receivers, those also have to be enabled for PIM. And the idea is the source and receiver signaling is processed by the FHR or the FHR or the LHR. But in order for them to take that signaling and convert it into PIM signaling, PIM must be enabled on those interfaces as well. So essentially, any interface in the topology, as we see the topology that has an IP address configured over it, that must be enabled for PIM. So that would be the easy way to go about it. Once PIM has been configured, PIM sparse mode has been configured on all of the PIM interfaces, the next prerequisite here is to disable STP switchover, and this will be done on the LHR. So by default, Junos, as well as iOS, so we saw this in the iOS demo as well, the default behavior is something called first packet switchover. So as soon as the LHR receives the very first packet over the star comma tree, it then has enough information about the source to start signaling S comma tree, and that is essentially what it does. Now the way to control the STP switchover is by manipulating the STP threshold. Now this is the rate of reception, how fast are you receiving packets, or what is the bandwidth of packets that are being received over the star comma tree. And if it exceeds a certain bandwidth by the STP switchover, that is the only time that the LHR then starts signaling an independent S comma tree. Till that threshold, the LHR is happy receiving all of the packets from radio or star comma tree. So if we essentially raise that threshold high enough, in our case we are raising it to infinity, then that threshold is never essentially met, and the STP switchover essentially is disabled, and that is what we really want to do in the end. Now in Junos, this is once again done under the protocol split hierarchy. So that is line with overarching theme of Junos, which is very hierarchical, so it's done under the protocol split hierarchy. To control which packets are actually subjected to the STP switchover, this threshold applies to which packets. Junos does allow you to be a little bit more granular, and you can achieve that granularity by having a policy. And this policy is essential, so that doesn't really work without the policy. So this policy will determine what type of sources, or what IP ranges of sources, what IP ranges there are, all of the different variables or knobs available there. In our case, because we really just want to give a blanket or disable ESP threshold or STP switchover completely, so blanketing all of the packets on the LHR. We have created a really, really simple policy here, which is all packet traffic. This is just the name of the policy, but what the policy does, it doesn't really have any terms. So it doesn't have really have match clauses in the only term that's here. So it matches all of the packets, and if it matches all the packets, it then accepts it for the purposes of the STP switchover, or the STP threshold being raised to infinity. Essentially, once this policy is tied into the STP threshold, it raises the STP threshold to infinity for all of the S collections. So all of the multicast traffic on this particular LHR will not be subjected to STP threshold, STP switchover, and that is our purpose. So these are the prerequisites. Now it's time to cover topology, going over fine points. It's not a very complex topology. But if you need more information about topology, that demo really is a prerequisite of this demo. So that demo introduces you to the topology. This topology is also...
Okay, so you said there's a demo that sets up this topology, so did I skip? Oh yeah, so it looks like I'm on demo 4.3. So... Oh no. Oh, that's dense mode demo. Oh my god, there's literally like 10 hours of information here. Sparse mode. Oh, I'm looking at, I'm looking at 4.1. So I've got 2 hours of prerequisite information. Oh no, cause these are iOS. So is there a 4.0 demo? No. Is there like a 3 point something demo? Dense mode, don't need to worry about that. I do need to worry about source specific mode. Don't say anything about that though.
So available for download in the actual.
But let's call from Virginia. That's a no-go. Okay, my phone is betraying me. I'm gonna put it in silent mode here. Alright, so let's see here. So we've got a topology like this. Let's just arrange the routers so that it looks the same. TA. Alright, and then I can listen while I'm doing this.
Description of the video, so it's highly encouraged that you go ahead and download the apology, follow it along. As the
Okay, so he's saying in the description of this video, here we go, perfect. We got a Dropbox. Thank you, this channel. This is a great channel. Perfect, so we've got everything here, nice and thorough. Okay. Perfect. So, yep, that looks good to me. Okay, and then we got, yep, so we'll need to wire everything up. Okay, and they're using encapsulation, or it looks like they're using VLANs. So let's do that. I haven't really gotten a lot of practice with VLANs on here, so let's just get comfortable doing that. Okay, and it looks like we've got two just hosts. So for that, I think I can just use, yeah, this VPCS host. Two of them. Alright, that looks good to me. So next step is going to be renaming all of these. I think I'm going to go and yeah, just make it look a little bit different than how he's got it there. Yeah, look like that. Okay, so now I'll bring up those two virtual hosts and then I'll rename everything here. This is just we'll call this host 1, host 2, host 3. Okay, and then I guess I'll keep the video running while I'm doing this.
That will make your life a lot easier as you follow along. The major network that is being used here. So if you look at all these links, they have the third and fourth octet identified there. They also have the actual IP address of the interfaces identified there. But the major network that is being used here is 172.26. So any of these addresses, they just begin with 172.26. For example, this one would be 172.26.12.0. 12.1 would be the IP address of R1. 12.2 would be the IP address of R2, and so on and so forth. Every single router also has a loopback. In the 0 subnet, it's /32 loopback, so 0.1, 0.2, and so on and so forth. When it comes to the actual PIN, as far as implementation, all of these interfaces, every single interface that has an IP address on this topology, other than loopbacks, every single one of these will be enabled for this function. That means all of these routers should be PIN neighbors. And we'll make sure of that before we go further into the demo. Also, pay attention to the LHRs. So the LHRs have two interfaces, each one has one. And also, our sub interfaces, they face the receiver, so those will also be enabled for this. Every single interface, that's the easiest thing. All of these.
Okay, he's going a bit beyond where I'm at right now, so let's just take it step by step. Okay, so that looks good to me. Next step is going to be to clear everything out, and then we'll go and do the precursor steps. I could automate this. It wouldn't take me that long to like have a server. Well, yeah, I don't know. Oh, I didn't. Okay, I gotta reopen them so that the new names show up in the tab. There we go. So there's something going on there. Okay, that's no big deal, just to redefine it. Yep, and then we've got the other set chassis on there, so this should be blanked out. It's going to serve as a host router. We won't need to worry about the VPCS, the virtual PC, quite yet. Okay, looks good to me. So virtual PC we can skip. Okay, this is going to be R1. Okay, so it's taking a long time to commit. That's usually a good sign. Let's just move on. This one has no config. Okay, that's a virtual PC, you can skip that. Okay, so good to go. Let's keep, well, you know what, instead of just watching the video, let's see if we can just use the notes here. I believe he said it was 172, dot 168. Oh, that's for MVPN, that's not what we're looking at. Okay, so let's just keep watching. Oh, okay. No, here it is. 172.26 for all of the...
Faces are also same bandwidth, so they're all 1 gigabit faces. There are no bandwidth mismatches at all in this topology.
Yeah.
So when it comes to STP switchover, we will see how TrueNAS routers will make their decisions now that all of the speeds are equal. So how will they go about the ECMP aspect of multicast? So there it is.
Okay, so he's going with 172.26, and then here's all his networks there. So I guess I want to say let's do that. Let's start with that. Okay, and let's make it easy on ourselves and start by just setting up descriptions. Did I have, I can't remember if I did a dash or a, I'll just do a dash. It doesn't matter. Okay, so moving on to router 5. All right, so I think that is enough. Yeah, that's all I've got left to do. I'm gonna save the hosts for later, for last. So he's going with 172.26 for all these. So let's take care of that next. It's okay, and now he's going with dot 1 and dot 12. So let's do that. So we're going to set VLAN tagging, and then we're going to set unit 1. Or we're going to go to edit unit 1. Set VLAN ID 1. Okay, family iNet address 172.26.1.0/24, unless it was 27. Nope, it was 26. Perfect. That looks good to me. Okay, and then he's got a loopback, and I think the loopbacks are following the same convention, 172.26. So let's set that up. Oh, this is interesting. How does that make any sense? Huh, it's interesting that these are all the same interface. GE00, and then this is GE00. So maybe they're all on a hub, or connected to a hub or something. I have no idea. Yeah, that's confusing, but it's okay. We'll just use different interfaces for each side, but we'll keep using VLANs even though they're not necessary. I just want some more practice with them. Okay, so we're gonna get a address on there. Oh, we've already got it, so let's move on to the next unit. Oh, but the next unit is going to be on a different interface. Nice. Oops, so I did 127. The correct one is going to be 172. Alright, so that looks good to me. We're also going to need some more prerequisites. We're going to need these added to protocol PIM, but I'll do the IP addressing first, and then I'll go back and do that next. The protocol PIM, adding it to the protocols. Okay, let's move on to, oh, what the heck? Alright, let me see what that error message was. Oh, I see. I did a dot. Oh, what the heck? Oh, I see. So the subnet is .0/24. This side's going to be .1. Oh, I think I forgot to enable VLAN tagging on it. Yep. What's the weather? I gotta check the weather quick to... Okay, yeah, that's what I thought. I just needed to know that because I gotta go somewhere soon, and I was planning to bundle up, but I didn't know if I actually needed to or not. Okay, so... Yep, moving on to router 2. Oh, okay, never mind. So this is going to be for router 3. So you can delete that. This is the going to router 1, so it's going to be 1. It's going to be unit 12, unit ID 12. Okay, and then we've got another one required for the port facing router 7, which is going to be 2. Going to be 27, VLAN 27. Okay, and then the port facing R3, which is router 0. It's going to be 2, 3. Okay, and then of course the loopback address. And we'll put a IP address on that. Doesn't need any VLANs or anything, so we can get started with the IP addressing now. Okay, so alright, so let's put the IP addressing on the interfaces now. Right? Is that right? Yeah, 1 goes to router 1, so next we'll do router 3. 0.23. Address is going to be 23.2. Okay, and now to router 7, which is going to be 2. 0.27. It's going to be okay, so it's going to be .27.2. Yeah, for a minute I thought that it was in the 4th octet where the 27 was, but nope, it's in the 3rd octet. Yeah, that looks good to me. It looks like we've got an extra unit 12 on here, so let's delete that. Okay, yeah, everything looks good to me. I don't see any problems. It's a bad omen. It means there might be problems. Alright, so let's move on to router 3. Takes this long to commit. Usually it's going to be fine. There we go. Okay, so let's move to router 7 next. Oh, and I'm starting to feel kind of strange. I don't know why. Oh, I know why I'm feeling strange, because I just all of a sudden out of nowhere started to feel hunger, and I hadn't been feeling any hunger until like just this moment, so that's why I feel so weird. Yeah, I really hadn't felt any hunger until now. All of a sudden I'm just randomly starting to feel hunger. I mean, it is 5. Like, I guess I would normally eat around this time, but I'm trying to eat fewer calories, so I'm planning to just eat. Like, yeah, I think I would normally eat around this time. So let's see here. We're going to do That's why I'm feeling hungry. But yeah, I'm doing something different now. I'm not gonna eat. I already ate. There we go. There we go. Okay, now let's do a run, show hint. Descriptions. There we go. Address dot 0.7 2 Okay, this is interesting. They're going with .7 on here, but let's follow their convention. I learned my lesson last time, and this looks like really great material, so I really have no reason to doubt the material here. Thank you to the person who created this, whoever you may be. Okay. Oh, nope. This is going to be .7 because I see. They're router 2 gets .2, router 1 gets .1, router 3 gets .3. Okay, so we're on router 7, and this is a /24. Okay, and then we've got 4.7. Looks good to me. Okay. Oops, so it looks like I made a mistake here. I configured, yep, I forgot to change this to a 1. So let's do a delete. Okay, oops, I did a set instead of a delete, so let's do a delete. Okay, and we'll go back and change it to a 1. And hopefully things look better now. Oops, so it deletes only the most specific part, so we're going to need to be more specific in what we want to delete. We want to delete the whole logical unit. Okay, so this looks a lot better now. Interface 0, unit 27, VLAN 27, 27 in the 3rd octet, 47 for unit 1, and then, yep, 7/32 for the loopback. Perfect. On to router 4. Alright, so we've got the VLAN tagging set up. So, yep, let's follow along. So the first one's going to be to router 3, which we'll do on G1, which will be unit 34, VLAN ID 34. Right, so then to router 7, we've got 0. Unit 47 with the VLAN ID of 47. Then we've got it to router 5, which is going to be 2. Unit 45, VLAN ID 45. Okay, and then we've got to router 6, which is 3, unit 46 to unit 46. Alright, looks good to me. Time for the IP addressing, so we'll start with the loopback. Okay, and moving on to the interfaces. So start with the interface to router 3. I'll get a fresh description here. So this is going to be interface 1, 34, family inet address, 34 dot, and then it's going to be .4. So convention makes a lot of sense to me now. really good convention. Next will be to router 7, which is going to be 47. Okay, router 5 has 45. Okay, and router 6 gets 46. Perfect. Yep, so everything looks good, no mistakes on this one. Might have some mistakes on the other one, but that's part of the fun of troubleshooting. I think that's part of what's going to get me better at doing this. So let's move on to router 5. And I've only got a half an hour left. Yeah, I don't know. I'm really racing against the clock right now. I don't know how things are going to work out for me, and I don't know if I'm tempted to move on from this subject, but at the same time I think it might demand more than just any particular subject. The topic in this might demand more than just 2 hours, which is all I was planning to give it. I mean, that just seems unreasonable for me to only spend 2 hours on PIM-SM. Okay, so back to, we've got unit 45, VLAN ID 45. Okay, and then we've got unit 50, is that 55 or 56? Oh, it's going to be 56. Perfect. Oh, nope, we're missing the IP addresses. So we'll start with the IP address to router 4. Okay, and then to the host. Looks good to me. Alright, next it's on to router 6, and then we'll be done with all the routers. I can just leave the hosts. I'm not sure how they'll be. I think they just need a simple IP. It's really not complicated. Routers are going to be the most complicated part. Okay, so the router 4, we're going to do unit 46, and then it's going to be VLAN ID 46, perfect, and then this is going to be unit, it's going to be interface 1, and we're going to have unit 56, VLAN 56, okay. Okay, so we've got family INET address 46.6/24. Looks good to me. Yep. And that's to, yep, router 4. So 1. Oh, and this is .56. And then it's 56/24. Yeah, I don't see anything wrong with that. Okay, so hopefully I've got it right. So that's good news. Let's move on to the next part. We'll keep watching the video. Oh, actually, we might need to go back and now do the prerequisites. So the prerequisites for all interfaces are set protocols PIM interface all mode sparse, and then we want to disable SPT switchover as well. Set protocols PIM SPT threshold infinity, and then I don't know what this means. Oh, I see. This is our policy option. So this is for all traffic. Okay, so let's chip away at that. And I've only got about 15 minutes. Maybe a little more than that, but okay. Okay, so set protocols PIM interface all mode sparse, and of course we have mode dense as well, but sparse is what's going to be on the test according to the curriculum. Alright, so now let's disable the PIM traffic. So set protocols PIM SPT threshold infinity, and then we'll call it all PIM traffic. Okay, so we'll need to create the policy, set policy options, policy statement, all PIM traffic, then accept. Yeah, that looks good to me. Let's do a show pipe display set, pipe no more. And yep, so we can just paste it in quickly for the next ones. So hopefully this commits. Yeah, looks good to me. So one by one, let's do it. I think I'm just going to open them all up, and then so that pasting, because it looks like sometimes I accidentally clear out my clipboard. I don't want that to happen. All right, perfect. So, yep, so now the next step will be given in the video.
So it doesn't have really match clauses in the only third that's here. So it matches all of the packets, and if it matches all of the packets, it then accepts it for the purposes of the SPP switchover, or the SPP threshold being raised to infinity. Essentially, once this policy is tied into an SPP threshold, it raises the SPP threshold to infinity for all of the S quantities. So all of the gas traffic on this particular LHR will not be subjected to SPP threshold, SPP switchover, and that is our purpose here. So these are the two prerequisites. Now it's time to cover the scenarios. Topology, going over fine points of that's not a very complex topology. But if you need more information about topology, that demo really is a prerequisite is this one. So that demo introduces you to the topology. This topology is also available for download in the actual description of the video, so it's highly encouraged that you go ahead and download the topology and follow it along. As the demo goes on, that will make your life a lot easier as you follow it. The major network that is being used here. So if you look at all the links, they have the third and fourth octet identified there. They also have the actual IP address for the interfaces identified there. But the major network that is being used here is 172.26. So any of these addresses, they just begin with 172.26. For example, this one would be 172.26.12.0.1 would be the IP address of R1, 12.2 would be the IP address of R2, and so on and so forth. Every single router also has the loopback in the 0 subnets, the /32 loopback, so 0.1, 0.2, and so on and so forth. When it comes to the actual PIM, source code implementation, all of these interfaces, every single interface that has an IP address on this topology, other than that, every single one of these will be enabled for bit source. That means all of these routers should be PIM enablers. And we'll make sure of that before we go further into the demo. Also, they feature the LHRs. So the LHRs have two interfaces. Each one of them has one. That also are some interfaces they face the receiver, so those will also be enabled for PIM. Every single interface that VTC is all of the interfaces are also same bandwidth, so they're all 1 gig interfaces. There are no bandwidth mismatches at all in this topology. So when it comes to SPP switchover, we will see how junior routers will make their decisions now that all of the speeds are equal. So how will they go about with the DCMP aspect of multicast? So there is DCMP here. If you look at R4 and if you look at the source, R4 has two equal cross paths to the source, DR7 and DR3. So it's going to be a little bit interesting in an S-common G3 signal. But initially there's only going to be a star-common G3. So for the star-common G3, one of the more important things then is the RP. And the RP in this case is R3. So R3 is sort of centrally located, and it will be configured as the static RP for every single one of the PIM routers. Also, the RP's IP address will be the R3 loopback address. So that's another thing to keep in mind. The R3 loopback address is the RP's IP address, and that is what should be configured on all the routers. Once again, it's highly encouraged to go ahead and run down the topology, and then we'll go over the demo sequence. It's a very short demo, and we'll bring you up to speed with what's happening here. Last thing I want to mention is this lecture series covers both Junos and iOS devices at different times. In this current topology, routers R1 to R7 are all Junos devices. The source and the receivers, two receivers down here, and the source up here, these are always iOS devices. But they're iOS devices in several levels. There's no line unicast routing on them, they don't essentially take place in the unicast routing, and they don't take part in the PIM processing either. So the source is literally just sends unicast packets and wait for the replies. And the receivers just have one IGN basically. They don't take part in PIM. That's really all there is about this topology. If there's anything else, I'll probably touch on it as the demo goes on. And demo 0, very, very important. I highly encourage you to go ahead and watch that demo. Next is time to take a look at the actual scenarios that we'll cover now that we've covered the prerequisites. So the actual scenarios that this lecture will cover are number one, the static RP configuration. So the RP information has to be shared by all of the routers, all of the main routers. In addition to the RP node that is supposed to have RP duties. So in iOS, it was the single node that was configured on all of the routers. Junos just a little different. So once again, we are under the protocols of RP. The sublevel here is RP. So once you go under RP, there is a migration point, and there is an option for the RP itself, which would be local. So the local option is used on the RP. The static option is used on all of the other routers, so all of the non-RPs. Next is the keyword address. So this is not the actual IP, this is just the keyword address. And finally, which IP out of all of the IPs configured on the RP will respond to all of the RP duties, star common G-joins, and resistance, etc. So essentially two maps, one for all of the other routers and one for the RP, but the static RP configuration is usually not that hard. The next scenario here is the receivers are present, but there are no sources. So we'll see how similar works when the receivers have signal there and then to join the star common G3 or receive traffic for the star common G, but there are no sources. So in this case, you'll only see the star common G and the root, which is the RP. The next scenario is exactly the opposite of this. In this scenario, we'll have an active source in the network sending on that stream, but no receivers are interested in that stream. So this will show you the registration process between the FHR and the RP, and we will find out that none of the other routers are really aware of the signal. So this is not give a guess. Next, we'll do 2 followed by 3. So the receiver will come online. It'll signal the LHR, the intent of what it needs to receive from the sources, and then the source will come back. So we'll see what is the order of operations. When the receiver comes online, first followed by the source. Next is exactly the opposite. So it's 3 followed by 2. So the source is already online, it is the gas line on the RP is aware of that source, and then the receiver is aware to receive those packets. The last thing is PIM, SP3 switchover, or shortest path 2 switchover. So remember, as a prerequisite, we have disable PIM SP3 switchover. So in the very last step, we enable SP3 switchover and we're trying to study what differences actually take place with or without SP3 switchover. This would be when an S on G3 will be signaled independently by the LHR. Those are all the scenarios. It is time to start working with actual devices. The very first thing we need to do is to ensure that the two prerequisites that we decided for this topology are being met. So right now on R1, and let's take a look at the current configuration of R1. So we'll show show protocols. And as you see, other than the trace functions, there are nothing else in here. Right now, there is no PIM really on R1. If you look at the other routers, R2, R3, R4, it's essentially the same story on all of those routers. There are some trace functions with debug style capturing, but there is nothing else PIM-wise that is needed on this. R5 and R6 are, however, different. So the second prerequisite that we had was to raise the SP threshold to infinity for all PIM traffic, and this has to be done on the LHRs. So the LHRs are the case. We'll see when one of them actually is actively involved in PIM. We'll see why. But really, both of these routers, R5 and R6, are both LHRs. So this is where that SPB switchover command goes. So that's why you see that command on both of those routers. So let's take a look.
Okay, so it looks like I only needed this SPT threshold command on 5 and 6. I added it to all of them. Now, does he have this in a more like, do I have to watch the video? Yeah, it kind of looks like I need to watch the video.
But again, what that actually means, so it is raising the SP threshold to infinity for all PIM traffic. So let's take a look at this policy policy statement, all PIM traffic. And there we go, that's all it has. It has no match clause, and it has the PIM except that it's accepting all of the, it essentially applies to all of the multicast traffic on here. R6 is the same story. So SP's threshold, or the SP switchover disablement, that has already been carried out. So that part already taken care of. So last route is R7, and once again there is now on here. The next thing we're going to do is to enable them for all IP interfaces. That command is very simple. Set protocols PIM interface all. Now this all keyword here means that every interface that has an IP is now enabled for PIM as well. So let's send this command out. And as usual, Windows will also run the configuration. So once we commit the configuration, we will see that this configuration now has applied everywhere. So if I say show protocols PIM now, we will see that all of the interfaces are now activated for PIM. We will also do some exec commands to verify that all of the interfaces are coming up and all of the neighbors are discovering each other. So the first command should be run show PIM interfaces. So as you can see on R1, there are two interfaces that are dangerous. Now this is the active interface, so this SP interface is not important in this logic. JNCIE-SP and JNCIE-SP. So on topology, the interface that is facing the source, so this is .1, and this is .12. The interface connect on R1 towards. Both of those are now enabled for PIM. And not only are they enabled for PIM, you also have the neighbor config. So don't expect this.
Alright, I'm going to open up all of these so that I'm more like quick. Yeah, I'm just going to follow along with what he's doing here.
See the neighbor on the source facing interface, but you do expect to see a neighbor where R1 and R2 are connected. You do see that. The next command here would be run show PIM neighbors. So there we go, there is one neighbor for R1. Now R3, if you look at it, has actually R4 has the most neighbors. It has 4 neighbors, so we go to R4 and verify that we see 4 neighbors. So we do see 4 neighbors right here. Those are neighbor addresses and the interfaces that neighbors were discovered on. So once again, that SP interface shows that those lines that you do the everywhere else you do see neighbors. What happens here is once as far as what is enabled on an interface, that interface will begin the hello discovery, the neighbor discovery process by sending hello messages out to its neighbor. And when we look at the structure of those messages, like Senator should also receive those messages from the neighbor that should have been enabled. So let's go ahead and take a look at these messages. And here's a typical hello message. So let's figure out which one is being sent by R1. Here is a hello message that is being sent by R1. You cannot determine the recipient just by looking at the destination. And that's essentially because the destination is that all PIM routers exist. So 224.0.13. It's a multicast address, and that's essentially to make sure that once you send that packet out, if it's a multi-access interface, then all of the neighbors that are connected on that interface will all receive this packet. So here, 172.26.12.1, that tells us which router this is emerging from, which router actually produced that. So the exit interface, or the outgoing interface, its IP is used as the source IP in the hello message. Let's take a look at the actual IP header of this. So the IP header, a couple of things to pay attention to. The TTL here, time to live, should be 1, which it is. Time to live is 1. And that means this is a linked local message. It is not going to be routed on R2. R2 will resolve this message, will discover R1, that is the end of it, because that is the whole purpose of this message. The protocol is 103, which is a well-known protocol for PIM, and the destination IP here is important. It's the multicast destination IP that essentially means all PIM routers. Finally, inside the whole packet, so first there would be the PIM header, and once again the version here is version 2. So for version 2, the type of hello message is type 0, it's the very first message in the text parse mode, so it's the number we see it. And then there are a few DLDs, like value option statements. So let's take a look at them one by one. The very first one is hold time. We've gone over this a couple of different times, but this is the amount of time a neighbor will wait for. So R1 is sending this hello packet out to all of its neighbors. 105 seconds is how long those neighbors will wait. So R1 will go down, but suppose the interface didn't go down. 105 seconds is how long those drivers will wait to hear from R1, to receive another hello from R1 before declaring R1 down. So a lost neighbor. So this is not different than, say, OSP dead time or EIGRP hold time. This is the same thing, but you're advertising it in the hello packet itself. Next option here is the LAN prone delay option. Now, this is not being covered in this particular demo. We may do such a short video on the LAN prone delay option because there are a couple of other options, a couple of other concepts that we need to discuss before we can get into the LAN prone delay. So we'll shelve that right now and perhaps cover it in a later video. Next option is the DR priority. The DR election, the designated router election, is essential in sparse mode. We will see in a second why. So every multi-access interface has to have one, so any Ethernet interface, for all intents and purposes, in sparse mode has to have a DR on it. So there has to be a designated router that is handling end duties for that segment. And we'll see what those duties are, but the election is first. So the election is carried out using this value of DR priority. By default, Junos just as iOS sets a DR priority of 1. So that means all the routers that are on a segment will be tied with the DR priority, and then they determine the outcome of the election using the highest IP. So they are also advertising their source IPs in the packet, so the highest IP lists. But DR priority can be manipulated to bias the outcome of this election. So by default, DR priority is 1. Generation ID is the final option here. And this is used for graceful restart of the PIM process. And what is going to happen here is if the PIM process restarts gracefully, that means the control plane went down, the control plane went through a reload, but the data plane was active throughout. After the restart, so suppose R1 restarts, after the restart of PIM, R1 will start advertising a different generation ID. So a completely unique and random generation ID. And as R1's neighbors receive these new hellos, they look at the generation ID compared with the stored generation ID, and they realize that that means R1 must have restarted gracefully, or must have restarted at least. What they try to do on their end is they try to backfeed all of the start-ONG, all of the S-ONG information back to R1. So they're backfeeding this information to R1, so R1 can then bootstrap itself to the state where it was in before it started. But how that bootstrap is detected is by using the generation ID. So this is the hello packet overall, look at the DoD options, and what you can see here is once I enabled this sparse mode on the routers, all of a sudden there was this bar of hellos. So the hellos were not generated before the was actually activated on the interface, which actually makes sense. Now that we take a look at the hello packets and how the DR priorities actually carry the hello packets, let's take a look at how that actually affects PIM sparse mode. So in PIM mode, we briefly went over the DR election, but we also noted that the protocol itself, PIM mode, which is a separate protocol in sparse mode, did not really need the DR election for the operation of the protocol. The reason the DR election was built into PIM mode was for the benefit of IGMP version 1. So IGMP version 1 did not have the concept of like the A designated carrier, and it depended on the PIM routing protocol, the Multicast routing protocol, really, which happens to be PIM in this case, the Multicast routing protocol to elect a designated router, and then that router became the designated carrier on that segment. PIM sparse mode still does that, so it serves that purpose, but the election of DR is also essential to the operation of PIM sparse mode. And oftentimes while troubleshooting, you'll realize that you need to be aware of what your DR is at a certain moment in order for you to troubleshoot the problem correctly. So in our case, this last hop segment here has R5 and R6 on it. And if you realize, so let's pretend this is going to happen later on as well. Let's pretend R1 or Reg 1, which is Reg 100, joins the group. So joins the server group. And once it joins that group, it is going to signal the last hop routers using IGMP. And the last hop routers, once they receive this IGMP, they have to then signal the start-ONG tree up to the RB. If both of these routers started doing that, so both of the last hop routers started signaling to start ONG tree, then what's going to happen from our force point of view, so at some point there are going to be two packets, or 2 separate multicast streams that come down to R5 and R6, and in the end, R5 and R6 can then send that stream over to Reg 100, and Reg 100, instead of getting one copy, it gets 2 copies of all the packets on the stream. So in order to make this process better, what's going to happen in PIM sparse mode is that the PIM signaling is only going to be carried out by the DR. So once the DR is elected, all of the routers on that multicast segment, so the DR concept really applies to this segment down here. And once all the routers on that segment are aware of the presence of the DR, they will then not bother to perform the PIM signaling. So let's take a look at R5 and R6. And so both of the DR priorities are 1. So we haven't changed the default. That means there's going to be a tie in that first election using DR priority as a tiebreaker. And the next criteria would be to take a look at the IP address. Well, 6 just happens to be greater than 5. So that means R6 will become DR. It will continue signaling PIM like it would have normally, but R5 will also know this information. R5 will know who is the DR on that segment, and R5 will not perform the PIM signaling. But R5 still has the IGMP state intact on it, and in case R6 was to go down, so later on R6 goes down, that means the signaling goes down, now R5 can take this IGMP information and perform the signaling, because now by being the only router left on the segment, it should also be the DR. The same thing applies to the FHRs as well. So if these devices were not receivers, suppose they were sources, they will also send multicast packets, and multicast packets will be received by both of the routers on that segment. But when it comes to the PIM registration message, only the DR will then form the registration message process through the DRP. So that part is very, very essential to PIM sparse mode. So it actually is one of the important things for troubleshooting or configuration of PIM sparse mode. now that we've actually fulfilled the prerequisites, it's time to move to actual scenarios. So the very first scenario here is going to be the static RP configuration. And with the static RP configuration, as was mentioned before, there is a separate configuration for the RP itself to make the RP aware of its own duties and which IP address to use for those, and a slightly different configuration for all of the other routers. What we're going to do here to keep things interesting is I'll go ahead and configure the RP. So we'll go ahead and configure the local option on R3 to make sure that it is ready to take the RP duties. But as for the other routers, I'm going to conveniently forget to program the RPs on them. And we'll move on to scenario 2 to discover what will happen if we forget that very quick step. And then we'll go back and finish it. So let's go on to R3 and verify what we have in place right now and what needs to be done. So here we are on R3. Let's take a quick recap of the show protocol again. And as you can see, there's only two things here. There's the fixed options to get all of the debugs, and there is the interface all those parts, so all of the interfaces as far as them. But let's go ahead and take a look at R3's interfaces. And specifically, I'm going to take a look at the loopback interface. So the loopback interface here is LO0, and it is 172.26.0.3. So that's going to be the ID for the RP site address. So now we can actually configure R3 to be a local RP. So say set protocol again, RP local, and then it's going to be the keyword address. So address, and which address we use is going to be this 172.26.0.3 address. And as you see, there's another option that we need here, nothing static, or static RP. So this is it for configuring a router to perform the static RP duties. Go ahead and make this. Now it's going to be run show PIM RPs. And there we go, that's our verification now. So RP address 172.26.0.3, it's a static RP, and it is the RP for all of it. So it's for the entire Class B of Multicast. So we will see in future videos how we can be more granular with this, but for right now, all of the prefixes in the Class B are all going to have the same line RP. Now, the next scenario will involve LHR, so let's quickly go to the LHRs and verify the same things. So we'll call it R6 is going to be LHR, it's going to be LHR DR. And for right now, there's one additional command here, and that's disable SBD, switch over. And other than that, all of the interfaces are on sparse. So if I say run show PIM RPs, there's nothing here. And this will become critical as I move to the next scenario. But for right now, R3 knows that it is the RP and it is able to handle those RP duties. So let's quickly move on to the next scenario, which is going to be receivers present, but no sources. So where are the receivers in our topology? Our receivers are Rec 100 and Rec 200, and they are down here on the bottom right. And let's join two groups here. So we're going to join 172, that would do very well as a multicast group. So all of the groups I'm going to join are all going to be in the 239 range. So 239 followed by the three outfits that are right down here. So Rec 100, let's go ahead and join 1.1.1. And on Rec 200, let's go ahead and join 2.2.2. And both of these are only going to be receivers. We don't have the source that is multicasting these addresses yet. The next step should be the IGMP joins, or IGMP should ports that are sent to laptop routers. So let's go ahead and see what's going to happen on the laptop routers. So here we are, back on Rec 100 and Rec 200. Now these are just Cisco routers, and if I say show what?
Okay, so, now we're on the VC, the virtual VPCS. So,
IP route. You see, they are not configured as multicast routers. So if I say show IP route, multicast routing is not even on here. Same thing for Rec 200, show IP route, just as one gateway, and show IP route, multicast routing is not even configured here. So they're essentially just IGMP receivers. They're receivers that signal using IGMP. So on Rec 100, let's go to the interface that is consequence, which will be the interface with this IP address. So I'll quickly say show IP 93, and that is gig00.66. I'll go to that interface. Now I'll say IP IGMP join group, and we'll join that 239 group.
okay, so there's a lot of complicated configuration on the host. I don't think it's as simple as just setting up, because I need IGMP. Can I configure IGMP on here? I might need a Cisco router. Yeah, I don't see any option for IGMP. All these join commands. So yeah, I'm gonna need to use a Cisco router. God damn it. Okay. And he says Rec 100. I'm not sure why he's using the term Rec, R-E-C. But we'll just go with host 100. Oh man, and I can't rename it when it's on. That's okay. It doesn't have to be named in the actual GUI. Oh, and it's 6:30. I gotta be somewhere, so I need to give myself enough time to get there. Yeah, I think this is gonna be it. Let me go ahead and do this share button. It should be at the bottom. Yeah, and let's say start at, copy. Okay, and then we'll add that to my notes here. This will be where I left off, so when I come back we'll keep watching from there, and yeah, that will be configuring the Cisco. So thanks for watching, and I'll see you in the next one.